Okay, welcome back for a little bit more into chapter 10. A little bit more on the chi-square to assess for relationships. Okay, so just wanted to mention, because it will be helpful for a later portion of the class, the following hypothetical table. I've got T is corresponding to tall people, so over 6 foot. S for short, under 6 foot. Play in the NBA, okay? B, play basketball professionally. N, do not. And so the chance that you are tall if you play in the NBA, you would think that would be pretty large. Of people who play in the NBA, what fraction are tall? A lot. Literally, tall, given play in the NBA, is tall and in the NBA over the number of people in the NBA. That's, shoot, A is almost A plus C. C is the number of short NBA players, people below 6 foot. That's not so many. So A over A plus C, okay? That's very different than the chance that you play in the NBA if you're tall. Of the tall people, there's tall in the NBA and tall who don't play basketball professionally. And my guess is B is a lot larger than A, so A over A plus B is going to be very tiny. The rate of playing in the NBA if you're tall is tiny, but the rate of being tall if you play in the NBA is quite large. Forgetting those two facts, confusing them, is sometimes called confusion of the inverse. Very common problem. Very common problem. So let's move forward into newish material. There's lots of ways of stating a null hypothesis, and maybe I'm going to sort of work from that in the context of Gregor Mendel's P's. There's Gregor Mendel's P's have, I guess, they're smooth or wrinkly, they're yellow or they're green, smooth, wrinkly, yellow, green, right? A lot of different ways of phrasing that, but Gregor Mendel would say, among the smooth P's and among the wrinkly P's, the rate of yellow is the same. I could also say among the yellow P's, the rate of smoothness is the rate of smoothness among the wrinkly P's, or the rate of green of the wrinkled equals the rate of green of the smooth. A lot of different ways I could phrase the exact same concept. They all basically say the same thing: independence between rows and columns. Which row you're in doesn't help me predict which column you're in, or vice versa. So what if we have a contingency table that is more than 2 rows and 2 columns? Here's one such contingency table. These are data from the Health and Nutrition Examination Survey of 2004. There were 2,237 individuals, and they were asked the question, M or F, and they were asked the question, right-handed, left-handed, or ambidextrous. And my null hypothesis is now, because it's more than 2 rows or more than 2 columns, has to be composite. Multiple equalities must appear in a composite hypothesis. I would say the concept of handedness doesn't depend on gender could be said the following way: the rate of right-handedness among the males is the same as the rate of right-handedness in the females, and the rate of left-handedness in the males is the same as the rate of left-handedness in the females, and the rate of ambidextrousness in the males is the same as the rate of ambidextrousness in the females. That's a lot of words. You could summarize that by saying the rates of various handednesses is the same between both genders. You could also say the distribution of handedness is the same in males and females. The alternative would be simply then the distribution is not the same. So it's, again, as before, chi-square, the sum of observed minus expected, and as before, the expected counts can be easily obtained. We'll skip over the degrees of freedom in a second, but I'm going to say I could easily find for the upper left cell the row total 2004 times the column total 1067 over the total of the whole table 2237. I get 955.86. I get one expected count. How do I get the other expected counts? Well, I guess if I know the total of the whole of the table, I'm going to go with green here. That one's for free. If I know the right-handers are 2004, I can subtract because I know something, male count plus female count of the expecteds equals then the total count for the right-handers. One upper left cell, the expected count was determined. Now my claim is I've still got 2 rows and 2 columns left. If I figure out the expected count there in a second location, that'd be 205, the row total, times the column total, 1067, over the total of the whole of the table, 2237. That is the rate of maleness, if you will. The thing in the parenthesis is the rate of males. What fraction are male? Of the 205 left-handers, if the same rate of maleness applies as to right-handers and ambidextrous, we would have then our 97.78 expected count. So if I have one expected count there in blue and a second one here also in blue, I'm thinking I could, again, via subtraction, get another expected count. And again, yet another expected count because those 3 need to sum to the male total, and then yet another expected count. So blue ones I have to get via the row times column over table total approach. Those circled in green are those that I could get via subtraction. That's how you know degrees of freedom, actually. Let's go back a page. Degrees of freedom is always in a contingency table, rows and columns. The number of rows minus 1 times the number of columns minus 1. I had 3 rows, subtract 1 from it, I get 2, times the number of columns, 2 minus 1, that's 2 times 1, overall 2 degrees of freedom. It turns out that once we have 2 in the upper left cells determined, the others are for free. 2 is the degrees of freedom. It's the number that we have to get by row times column over total of the whole of the table. So my chi-square value is O minus E squared over E, 11.8 with 2 degrees of freedom. I get a p-value between 0.001 and 0.01. Verify that you could get this before we move forward. Let's do this. 2 degrees of freedom, and I had 11 as my chi-square value. 2 degrees of freedom, 11 as the chi-square value is right there. So the p-value, the upper tail area, must be between 0.001 and 0.01. Your conclusion is going to be easy. Your conclusion is that you think there is a relationship, that there's a difference between males and females in terms of the distribution of handedness. Quite easy. Let's dot some I's and cross some T's in those later bits of chapter 10 here. Smoking and drinking physicians, I happen to have these data in, boy, you don't want to do this with, 3 rows and 5 columns, 3 times 4, well, no, so 3 minus 1, that's 2 times 5 minus 1, 4, 8 separate, 8 degrees of freedom. My gosh, that's annoying. 1, 2, 3, 4, 5, 6, 7, 8 separate expected counts have to be determined by row and column stuff. Not what you want to do. Fortunately, if you have software that tells you things like the same table, you can get the expected counts for free. You get your chi-square test, the Pearson chi-square for free, 464, and your p-value less than 0.0001, you quickly know that there's a relationship. You quickly know that there is a relationship. Okay, so I want to introduce the concept in mind of where is there a tendency towards the issues. I'm sorry, where is the distance? Oh, shoot, how do I phrase this again? Again, I'm being distracted by people in my household. Where are the observed counts quite different from the expected counts? Okay, the observed count of 296 in the current smoking, drinking 5 to 6 drinks per week, we had an expected value of 271. I saw 296. That is a fairly large value. If I were to, under my contingency table, just let me grab my glasses again. In my contingency table down here, I could display not just the expected counts, but what are sometimes called the deviations. Where are those differences? Now, these deviations, they're sometimes called the unstandardized residuals as well. A positive means what I saw was above what I expected. Negative means what you saw is below what you expected. These deviations are the numerators in the chi-square value before you square it. Large deviations in absolute value are where the differences are huge. Right there is a difference that's huge. If I were to also show you the cell chi-square value, this is the contribution to chi-square from a particular cell, okay? So the observed minus expected squared over expected, in this case is 1.7. The observed minus expected just alone is the negative 30. So the sign here in this third row, the deviations, whether it's above or below, whether the expected, whether the actual count is above or below the expected, and then the chi-square contribution, you look for large chi-square contributions, and that's where your chi-square value is coming from, okay? 106 is a huge chi-square contribution. What you're seeing is the following. Among doctors who've never smoked, I expected only about 3,000 to have a low alcohol consumption rate. I saw 3,500, a sizable difference. Doctors who don't smoke tend to not drink. That's really what we're seeing. Positives over here, okay? Positive over here. That's the idea behind these other terms, the chi-square contribution and then the deviation themselves. Okay. One last thing that we need to talk about in our chi-square section here, and that is what do you need to be reasonably true for your chi-square procedure to be reasonable? One of them is design conditions. Either we're sampling for one population, doctors, and we got a simple random sample, and we categorize them based on their smoking and their drinking preferences. Or perhaps I could have a simple random sample from the rows, or a simple random sample from the columns. Stratified samples work just fine. If you have a sample size condition, we usually say we need a large N to do one of these procedures. A large enough sample that you have an expected count of at least 5 everywhere. Expected counts always at least 5. If you have an expected count below 5, then you shouldn't be using the procedure. Okay, that's a good place to stop. Enjoy the rest of your day, and we'll see you in the future. Bye-bye.